Hello students, welcome to this new normal situation under COVID-19. I am Sudipto Das, lecturer in physics from Shekhpara ARM Polytechnic. Today I am going to discuss physics subunit 3.3, that is friction. In this chapter, I am going to discuss the concept of friction, types of friction, laws of limiting friction, coefficient of friction, reducing friction, and some of its engineering applications, and the work done in moving an object on a rough inclined plane. Now, what is friction? Whenever two bodies are in contact, that is touching each other, then they exert force on each other. These forces are known as contact forces, and the component of the contact force, which is parallel to the surfaces in contact, is known as force of friction or simply friction. Here I have shown that two blocks are there. One is blue and the other is white. Blue is resting over the white block, and it gives its weight on the white block as gravitational force Fg. On the other hand, due to Newton's third law, the white block gives normal reaction force Fn. Now, if we apply force F, the frictional force Fs comes into play, which is parallel to the contact surfaces. This is the friction force. And a popular example is the matchbox and the matchstick. When a matchstick is struck over a matchbox, we get fire. Because of the frictional force between the chemicals in matchbox surface and the matchstick, the force of friction is produced and we get fire because of the frictional force. Now, how it is created? If we go to the microscopic view of two surfaces going over each other, suppose the shoe sole and the ground, we can see that very few points are actually in contact. Most points are crests and troughs, which are interlocking and prevent the going over each other. And in the microscopic view, we can clearly see the bumps and holes crash into each other when they go over each other. This causes the frictional force. What are the types of friction? Types of frictions are static friction and kinetic friction. From the name, it is clear that static friction comes into play when a body is at rest. To initiate the motion of the box, the man on the left of the slide must overcome the force of static friction. And the force of static friction keeps the stationary object at rest. From the diagram, we can see again that the force of static friction, Fs, is directly proportional with the normal reaction force Fn. So from mathematics, we can write that Fs equal to some constant μs multiplied by Fn, where this μs is called the coefficient of static friction. In a similar way, kinetic friction can be explained. Suppose this baseball player is sliding and comes into stop. Upon sliding, the player will come to a complete stop due to the force of kinetic friction. Once the force of static friction is overcome, the force of kinetic friction is what slows down a moving object. So, the friction is the given here as the force of kinetic friction. It is also proportional to the normal reaction force, and it can be given by Fk equal to some constant mu k into Fn, where mu k is called the coefficient of kinetic friction. So what are the types of kinetic friction? One is sliding and another is rolling friction. What is sliding friction? Sliding friction is a friction force that opposes the direction of relative motion that occurs when solid surfaces slide over one another. That is, friction force always prevents the relative motion between the two surfaces. There may be two surfaces, both surfaces are moving. One have the greater velocity, another may be the lower velocity. The greater velocity surface is prevented by the relative motion's frictional force. That is, the friction force prevents the motion of the greater velocity surface. But on the other hand, it directs in the same direction of the lower velocity surface. So in this way, we can say that somewhat it is the frictional force prevents the relative motion between the surfaces. So what is the example of sliding friction? Writing over pencil point and the paper. Here the paper is fixed, but the pencil on the or the pen is moving. So the relative motion between the paper and the pen is prevented by the sliding friction. Another example is combing your hair, where the surface of comb and the strands of hair going over the sliding friction. Another type of friction, rolling friction, is the friction that occurs between surfaces in motion that are rolling, in which one of the surfaces is a wheel, a roller, or a ball, that is a spherical surface. You can see the example of the game where a spherical ball is thrown to the white stands and it will strike the stands. Many of the stands will go down and the player gets more points. So examples are riding a bike where tires and the ground goes into the rolling friction, and the bowling in the cricket where ball and the pitch or the lane going over the rolling friction also. Another type of friction we can give here as an example, which is fluid friction. What is fluid? Fluid is that type of matter which can flow, that is, liquids or gases. So fluid friction is the force that tries to slow objects down when they move through a liquid or a gas. It is also known as drag or fluid resistance. You can see in the picture a glider is moving through air, an aeroplane is flying, and a swimmer swims in a pool of water. All are going through the fluid friction. So objects while moving through gases and liquids, that is fluids, experience such fluid friction. Fluid friction increases as the speed of the object increases. The object, that is the glider or the aeroplane or the swimmer, if increases their speed, then fluid friction also increases. An airplane, a glider, and a swimmer all experience this fluid friction. Two things here is very important to explain. One is angle of friction and another is angle of repose. Now, angle of friction in the above diagram, it is the angle made by the resultant R of the normal reaction force N and limiting force of friction F, and made with the direction of normal reaction force. If R is the resultant of normal reaction force N and force of friction F, which is equal to mu s into N, then R can be written as root over N square plus F square. If theta is the angle of friction here, then we can write tan theta equal to F by N, and that is also equal to mu s, or theta equal to tan inverse F by N. So we get that the angle of friction equal to tan inverse of F by N. Now, what is angle of repose? Angle of repose is that angle which is made by the inclined plane with the horizontal when a body resting on an inclined plane is just on the verge of sliding, but it is not sliding actually. So the minimum angle made by the inclined plane with the horizontal surface such that the body lying on the inclined plane is just at the verge of sliding down along the inclined plane is called angle of repose. This is possible if alpha be the angle of repose, limiting force of friction F equal to mg sin alpha and normal reaction force R equal to mg cos alpha. So F by R equal to tan alpha, but tan alpha equal to mu s, that is coefficient of static friction. Thus, coefficient of static friction is numerically equal to the tangent of the angle of repose. Again, we can see from the previous angle of friction that mu s equal to tan theta, where theta is the angle of friction. Also mu s equal to tan alpha, where alpha is the angle of repose. So tan theta equal to tan alpha, or simply theta equal to alpha. So we get angle of friction equal to angle of repose. Now I am going to discuss some laws of limiting friction. 1. The direction of the force of limiting friction is always opposite to the direction in which the motion takes place or tends to take place. That is, the force of limiting friction always prevents the relative motion between the bodies. 2. The force of friction acts tangentially along the surface of contact of two bodies. It is the tangential force acting at the surface of contact of the two bodies. 3. The magnitude of the limiting force of friction is directly proportional to the normal reaction force between the two surfaces. That is, Fs is directly proportional with Fn, and we get from the previous slide that Fs equal to some constant into Fn, which may be for static friction mu s, coefficient of static friction, or in the case of kinetic friction, it is mu k into Fn. Number 4. Limiting force of friction is independent of the area of the surface of contact of two bodies as long as normal reaction is constant. That is, if we do not replace the bodies which have more weight or more mass, then limiting force of friction is independent of its area of contact. It may be of larger area or small area, it does not depend. And 5th, limiting force of friction depends on the nature of the surfaces in contact. The nature of the surfaces, if it be smooth, then friction is less. If it be rough, then friction is more, because more points go on crests and troughs. Here we plot a graphical plot between force of friction and the applied force. In the first part, there is static region. In the second part, we have explained the kinetic region. In the static region, when a force is applied on a body at rest, a force of friction called static friction comes into play. The static friction opposes the applied force to cause the motion of the body. On increasing the applied force, static friction also increases proportionately and becomes maximum. This maximum static friction is called limiting friction. Up to this point, so static friction is directly proportional with the applied force. Now on the second part, when the applied force is increased beyond the value of limiting friction, the body just begins to slide over the surface on which it was resting. At this stage, the static friction is converted into kinetic friction, which is less than the static friction. So the graph slightly downs here in the kinetic region. So I have compared these two coefficients of friction. One is coefficient of static friction, another is coefficient of kinetic friction. And the limiting force of friction, that is Fs max, is directly proportional with the normal reaction force Fn, or Fs max equal to some constant mu s into Fn, where mu s is called the coefficient of static friction. And Fn is equal to mg, so we have mu s equal to Fs max by mg. You can take a numerical example. Find the coefficient of static friction if 5 Newton force acting horizontally on a block of mass 2 kg resting on a horizontal surface is needed to just start the block moving over the horizontal surface. Take g equal to 10 meter per second square. And coefficient of kinetic friction in a similar way, we can explain that coefficient of kinetic friction can be get from the coefficient force of kinetic friction, which is proportional with the normal reaction force. So Fk, force of kinetic friction, equal to mu k, constant of proportionality, into Fn, where this mu k is called the coefficient of kinetic friction. And again we know that Fn equal to mg, so mu k equal to Fk over mg. Take also a numerical example. Calculate the coefficient of kinetic friction if 2 Newton force is needed to move a block of mass 2 kg with a constant speed over the horizontal surface. Here the block is moving, so you will get the force coefficient of kinetic friction. Here also you can take g equal to 10 meter per second square. For your interest, I have given a chart of comparison of some values of mu s, mu k and mu r, that is the coefficient of static friction, kinetic friction and rolling friction. So you can see that steel on steel when dry, the mu s is 0.9, mu k is 0.8 and mu r is 0.002. So mu s is greater here, mu k is in between the mu s and mu r is very less. And steel on steel when lubricated, all the coefficients decreases. That is mu s 0.1 and mu k 0.05, because the frictional force reduces due to lubrication. Here you can see the rubber on concrete. What is this in dry case? That is the car tire over the road. So coefficient of static friction is 0.9, but when it is rolling, it becomes 0.7 and 0.02, and when the kinetic friction sliding, it is 0.7. If it is wet, that is the surface or the road is wet due to rainy season or some water, then all the frictional coefficients decreases. You can see that 0.7 becomes the mu s and 0.6 is mu. An interesting example of synovial joints in humans, where some synovial fluid means, or the bone joints, where bone is moving when static friction coefficient is 0.01 and the kinetic friction coefficient is very much less, 0.003. Now, how we can reduce the force of friction. Friction can be reduced by making the surface smooth by polishing. You can see in the park that the slide, the children are playing on the slide or sliding on the slide. If it is polished, then they can move smoothly or fast on the slide to the downward position. Friction can also be reduced by applying lubricants like oil or grease to the rubbing surfaces. You can see the mechanic uses grease in moving parts of its machine to run it smoothly, or a few oil drops of oil on hinges of door smooths its movement. While playing carom board, you sprinkle boric powder on carom board so that the carom and the striker can move very easily. In a hovercraft, it is a transportation thing which have a cushion of compressed air provided by the downward blast reduces the frictional drag, which can move both on the surface of ground and also on the water. The third point can be friction reduced by wheels to move objects. Heavy objects like the trolleys, you can see that in the airports or on the station or bus stop, you move the trolleys fitted with wheels. Why? It can be pulled easily over surfaces because the sliding friction is converted into rolling friction while the object is on wheels. And the rolling friction is less than the sliding friction, so the moving becomes very easy. And the friction can be reduced by using ball bearings between moving parts of a machine. What are ball bearings? Ball bearings is a device which consists of a ring of small metals balls which can roll freely. They are designed to make the moving parts of a machine to roll over each other rather than slide. In such a way, rolling friction takes over sliding friction so as to reduce friction. To reduce the friction between the central hole and axle of a wheel, wheels are mounted on ball bearings, which is fixed between hub of wheel and axle. When the wheel revolves, the ball of ball bearings rolls and reduce friction. It's a simple example of rolling friction is less than the sliding friction. Here we can get some engineering applications of friction. I'm going through this very fast because you can see it from the slide. On first example, ladder friction. You can see the ladder resting on walls and the floors, and you can calculate the position of the ladder, where it will be rested so that it does not moves down or falls down, and you can calculate the various resultant force to calculate its position. Another example is wedge friction. Wedge friction, what is wedge? A wedge is used to lift loads vertically by applying horizontal force. These are made in triangular or the trapezoidal shape, which I have shown in the diagram in the downward direction. A triangular shaped wedge is moved so that the rectangular shaped body is moved upwards. Another example is the driver and the follower connected over a belt. Driver drives the follower with the help of the belt. The power is transmitted from one shaft to another by friction between the belt and the pulleys on which it passes. The driving pulley pulls the belt from one side and delivers the same to the other. So we can calculate the work done by this and the power transmitted through the belt. And another example is screw friction. The friction in the screw threads is widely used for fastening of components in machine and structure. The fasteners such as studs, bolts, nuts, and screws are very widely used. Screw friction is also used in the design of lifting machines. You can see when the car tire is punctured, the mechanic or the driver uses a screw jack to lift the heavy car, and he replaces the punctured tire with a new one. Square threads are used in screw jack, which is a machine used for raising or lifting of heavy loads by applying a small effort. The screw jack works on the principle of inclined plane. It is also a familiar example of friction in engineering application. Now we are discussing the work done in moving on rough inclined plane. Here we can see in the first diagram, the body is moving. So here the coefficient of kinetic friction comes into play. Equating the various forces along the inclined plane and normal to the inclined plane, we can see that mg sin theta is parallel component of weight and mg cos theta is the normal component. So N equal to mg cos theta, or frictional force F equal to mu k times mg cos theta. So the total force F, which can be applied to move it upwards on the inclined surface, F equal to mg sin theta plus mu k mg cos theta. So what is the work done? Work done is the force into displacement. So it is equal to mg sin theta plus mu k mg cos theta over bracket into the displacement s. And while it is moving down the inclined plane, we can see the frictional force F equal to mu k r equal to mu k mg cos theta again, and mu k is the coefficient of kinetic friction. So net force in the forward direction, that is in the downward direction over the inclined plane, is F equal to mg sin theta minus mu k mg cos theta, because these forces are opposite. Now let the distance traveled is s, so work done equal to force into displacement. So the work done we can calculate from here, W equal to mg sin theta minus mu k mg cos theta over bracket into the displacement. Thank you for your patience, and this is the end of the explanation here. Thank you once again.